In this mini lecture, we will derive another lateral directional stability derivatives, CNY, which is a Yawing moment change due to rate of yaw. Similar as the stability derivatives we've derived before, this CNR also has several contributions. One is contributed from the fin, the other is contributed from the wing. And in this slide, we'll look at the fin contribution to CNR. Again, we have this aircraft, and we can see the scenario is the aircraft is yawing towards the right at the rate of r. Okay, so now we are focusing on the fin, and we can see a velocity vector v, true airspeed of this aircraft. And because of the yawing motion, there will be a side velocity r times lf. And this velocity vector is pointing towards the left, and the LF is the distance between the aerodynamic center of the fin and the center of gravity. Okay, so in total, and this side slip velocity will contribute to a small angle of attack, delta alpha. Okay, and since we have an angle of attack, then there will be a side lift acting on the fin, which is YF. The task now is how to derive YF. Okay, so first we know delta alpha is R times LF divided by V, and we are quite familiar with how to derive delta alpha, right? So in here, we again assume delta alpha is a small angle. And then we can just write down YF, which is a side lift force acting on the fin and pointing towards the right. So it equals AF times delta A, delta alpha times half rho V squared times SF. So alpha F is lift force slope, fin lift force slope, and delta alpha is the angle of attack. And then we alpha AF times delta alpha is lift coefficient. Then we need to times half rho V squared times SF. Okay, and then we just plug in delta alpha. We have this relation. Okay, so we can tidy it up, becomes this. So we know YF. Since we are looking at the yawing moment, which is N, then we can know that this YF, since it's pointing towards the right, and then that will produce a negative yawing moment N. Okay, so now we can write down N, which is negative YF times LF. And pay attention to this negative sign. Why we get the negative sign? Because it follows the right-hand system. So we just plug in YF, then we can get this relation. Okay, and since we're looking at the derivative, partial N, partial R, so the R is eliminated, and then we find the denominator to get the non-dimensional CNR. And then we have this minus AF times SFLF divided by SB times LF divided by B. And we've seen this before. This ratio, we call it fin volume, and eventually CNR equals minus AF times VF times LF divided by B. We've derived the fin contribution to CNR. Now let's see how the wing contribute to this parameter. Again, we have this aircraft. It's yawing at a positive rate of R, and so let's see what happens on the wing. Okay, and the left wing, apparently because of the yawing motion, it's going forward, and the right wing is going backward. So we have forward going wing and a backward going wing. And in this case, the forward going wing apparently will move faster, and the backward going wing will move slightly slower. Because of the difference in moving speed, the velocity of left wing and the right wing, so the faster moving wing will produce a larger drag in comparison to the smaller, slower moving wing. So the left wing will have larger drag, will while the right wing will produce less drag. So in total, what can we imagine? In total, then there will be a negative yawing moment produced. So is that right? Now you can take out your right hand, and we can see the yawing moment N is pointing out of the screen. So that's how, under positive rate of yaw, how a negative yawing moment is produced. The task now is how can we write down N? Okay, so we know how the yawing moment is produced by the drag, and now we need to derive it, how to write it down. And again, we need to look at an incremental section on the wing. So we assume it's located on the right-hand side wing, and it's located at y, and the width of that incremental section is dy. And for that incremental section, the velocity is v minus ry. So we need to extract the induced velocity due to the yaw rate. Okay, so then we can write down the incremental drag. So it's minus cd times half rho v. And now the v is v minus ry square, and then times cy times d. Cy is a chord, and we should know for general wing, the chord changes along the span. Okay, so in order to make the derivation more straightforward, now we assume C is a constant. It's a rectangular wing, then the C is constant. Okay, and if we compare the two relations of dd, the incremental drag, we can find the second one has expanded version of v minus ry square, and you may notice r square and y square is eliminated because we applied the small disturbance assumption, which means r is much smaller, smaller value and smaller rate, and then ry is much smaller than v, so their square is much smaller than v square, so eventually we can eliminate it. Okay, now we work on the second incremental drag, and since we have the drag, and then we can just times its moment arm y, so we get the dn incremental yawing moment. And you may notice there's a negative sign in dn. That's because the yawing moment produced by that incremental section on the right hand side is negative. Okay, and then we just do the integration from minus half b to half b, and I'm not reading this integration. And in this equation we just tidy up, and so we get c minus cd times rho cvr times the integration against y square. And because y square is second order, and then the integration is symmetrical, we can just do half of it. So eventually, if we do some tidy up, it becomes minus cd rho v rc times b cubed divided by 12. So this is a wing contribution to the n. We've derived it. And then we need to, since we're looking at CNR, we still some steps to go. Okay, so that's the n, I'm pasting it here, and then we just do the derivation, nr, so the r is eliminated. And so CNR, we need to find the denominator, which is half rho v s b square. So eventually it's minus cd over 6. So that's the contribution from the wing. And I would say this procedure is exactly the same as CLR, which is a yawing rate give rise to the rolling moment change. Okay, so far we've derived the CNR. Remember, the derivation is on the rectangular wing, so this only applies to a rectangular wing, but in reality, not every aircraft has a rectangular wing. So this derivation is approximately alright for CD0, but the induced drag is subject to some complications. What is CD0? CD0 is the drag coefficient at their angle of attack. And some researchers have shown that this contribution, that means the wing contribution, is best presented by the following relation. So CNR is approximately minus CDI divided by K, and the K is a parameter. And for different, and it changes with aspect ratio. And for a large aspect ratio wing, for example 10, and the K is smaller, which means the CNR is larger, CNR contribution is larger. For a smaller aspect ratio wing, K becomes larger, then CNR is a smaller contribution. Okay, so for typical aircraft with an aspect ratio of 6 and a CL at 0.4, the wing contribution CNR could be minus 0.007. So it's a very small contribution in comparison to the fin contribution. So in total, this CNR can be expressed by the fin contribution, and later part is a wing contribution. So for the fin contribution, it's really less than minus 0.1, and in comparison, the fin contribution is less important, but it becomes more important when CL increases. So now we can close this derivation for CNR, and I hope you can also relate the wing contribution with respect to the CLR. That helps us to understand. One is for lift, for the lift, the other is for the drag.